Welcome back to Derivatives and Risk Education. In our previous video, we looked at the one-period binomial model. We derived the intuitive option pricing formula shown here. If you missed the previous video, it is worth a watch, as today we are going to build on the knowledge from that video and extend the one-period model to many periods with the multi-period binomial model. Like in the previous video, we suppose the stock starts at S0. Each period it either goes up and multiplies by the up factor U, or it goes down and multiplies by the down factor D. The full two-period tree would look like this. Note from the middle node at time 2 that an up move and then a down move equals a down and then an up move. We call a model with this feature a recombining tree. In general, after T periods with K up moves, the stock price, written as S subscript TK, is equal to S0 times the number of up moves U to the power of the number of up moves K times D to the power of the number of down moves, which is T minus K. So, for example, with S0 equals 100, U equals 1.2, and D equals 0.8, S21, so at time T equals 2, and with K equals 1, so with one up move and one down move is equal to 100 times 1.2 times 0.8, which equals 96. For our later examples, we will use this tree extended to 3 periods. Full details for this are in the attached spreadsheet. In the one-period model from the previous video, absence of arbitrage gave the risk-neutral probability P as 1 plus R minus D divided by U minus D, where R is the risk-free rate. We'll use this now also at every step of the multi-period binomial tree, with a risk-free rate R of 5%, and again U at 1.2 and D equal to 0.8. Plug in the numbers and get P equals 0.625. We'll be using this value for P for the remainder of the video. We will now look at 3 ways to value an option in a multi-period binomial tree. First, we'll derive a multi-period pricing formula based on discounting expected payoffs. Second, we'll see how we can use backward induction to work backwards through the tree from the final payoff. And finally, we'll use replication of the option with the underlying stock and borrowing. So, we'll start with the derivation of the pricing formula. Now at maturity, where the time T is equal to big N, which is the number of periods in the tree, the stock can take values of S0 times up factor U to the power of the number of up moves K times down factor D to the power of big N minus K for values of K from 0 to N. Probability of exactly K up moves is binomial, so it equals the standard expression for a binomial probability. Therefore, we can write the time 0 option price as the discounted expected payoff given by this formula. This is the multi-period extension for the one-period pricing logic which we derived in the previous video. Let's break down this formula. For a tree with n periods, the number of up moves K could be anything from 0 to n. So, we calculate for each possible value of K the payoff at time n multiplied by the binomial probability of this payoff occurring. Then, we sum up all these values for probability times payoff. Finally, we discount back from time n to time 0 at the risk-free rate to account for the time value of money. Let's look at an example of this expectation method with a tree with 3 periods for a European call option with a strike price of 100. As in our earlier example, we'll use a starting stock price of 100, U equals 1.2, D equals 0.8, and a risk-free rate of 5%. We're using a strike price K of 100, and we will look at a binomial tree with n equals 3 periods. As we saw before, this setup gives a risk-neutral probability P of 0.625. Then let's work out the terminal stock prices and payoffs. With 3 up moves, k equals 3, so the stock price there is after 3 up moves 100 times 1.2 to the power of 3, which equals 172.8. In our call option, we have the right to buy at 100. So this option here is worth 172.8 minus 100, so 72.8. Similarly, for k equals 2, so 2 up moves and therefore 1 down move, the stock price is S0 times 1.2 to the power of 2 times the down factor 0.8, which equals 115.2, so the call option payoff is 15.2. Then with only 1 up move, k equals 1, the stock price is 76.8. This means the call option's right to buy at 100 is worthless, so the payoff here is 0. And in the same way, for k equals 0, the stock price is also below the strike price, so again, the option payoff equals 0. As the payoff is 0 for k equals 0 and k equals 1, in the remainder of the example, we will only look at k equals 3 and k equals 2. Then, the binomial probabilities for each of the possible values for k are calculated using this formula and the value for p of 0.625. So the probability that k equals 3 is 0.2441. For k equals 2, the probability is 0.4395. This gives us all we need to calculate the expected payoffs as payoff times probability. So for 3 up moves, the payoff of 72.8 times the probability equals an expected payoff of 17.77. And in the same way, for k equals 2, we can calculate the expected payoff as 6.68. Then we sum up over all values of k, which gives the total expected payoff 24.45. That is the payoff at the expiration of the option at time t equals 3, but we want to know the value of the option at time t equals 0. So we discount the payoff for 3 periods at the risk-free rate of 5%. So we've used the expectation method to work out the value of this call option as 21.12. Full details of this example can be found in the attached spreadsheet. So that was one method we can use in a tree. Another method is known as backward induction, where we compute values recursively, meaning we start from the payoff at expiration and work back to time 0, 1 period at a time. At any node tk, so at time t, with k up moves so far, the option value equals the discounted risk-neutral expectation of its 2 children, which is given by this formula, which is the 1 period formula from the previous video applied locally. Repeating this formula backwards at each node from the expiration of the option to time 0 recovers V0. Let's see this in action in our example. Basically, backward induction just mirrors the 1 period logic at each node. For example, at t equals 2, with 2 up moves, V22 can be computed using this formula as 48.76. Working all nodes back to time 0 yields the same root price as we saw before, 21.12. The spreadsheet shows every node value computed this way. Then for the final method, replication. The previous video about the 1 period binomial model, we showed how we can replicate any option payoff with a portfolio consisting of some amount of the underlying stock and borrowing or lending. We can use the same argument here in a multi-period model. At node tk, choose delta shares and B in the bond, so the portfolio matches the option 1 period ahead in both states, using these formulas. If any of this is unfamiliar to you, it is worth watching the 1 period video again. From these formulas we can solve for the hedge delta and cash amount B. Rebalance at each node to perfectly replicate the option. Full derivation of these formulas was done in the 1 period video. Let's look at this for time 0 at the root of the tree. We can replicate there between nodes 1, 1 and 1, 0. Using the time 1 stock and option prices in the up and down scenarios, we can calculate delta as 0.672 and the amount to borrow B as 46.05. We can interpret these values as follows. To replicate the call option, we need to hold about 2/3 of a share and borrow 46 at the risk-free rate. The spreadsheet lists delta and B at other nodes. I've attached a Google Sheets file with every calculation, the full stock tree, backward induction at every node, binomial probabilities, replication portfolios, and more. The link is in the description so you can explore all the details yourself, verify each step, and adapt parameters. So that's the multi-period binomial model. We looked at a recombining stock tree, risk-neutral pricing by expectation, equivalent backward induction, and finally dynamic replication. In the next video, we'll build on this foundation. Don't forget to like and subscribe, and I'll see you in the next video.